Children, Unit 1 and Chapter 2. It is about electrostatic potential and capacitance. Electrostatic potential, it represents the degree of electrification of the body. Good morning, children. In the first chapter, we have learned about field and force. Both these quantities are vector quantities, whereas electrostatic potential is a scalar quantity. Both field and potential, they are the characteristic properties of any point in a field. Field, force, and electrostatic potential, they are very similar to the terms that we have learned in gravitation. Gravitational field, gravitational force, and gravitational potential. Difference is that in gravitation, in gravitational force, always it is an attractive force because it deals with mass. Whereas in electrostatics, the electrostatic force, it can be attractive or repulsive depending upon the sign of charge. So the very first topic that we are going to learn in this chapter is electric potential and electric potential difference. Potential word itself signifies work done. So the base meaning and the base formula for electric potential is the amount of work done to bring a unit positive charge from infinite to point P as given in the diagram. The notes which is given in the school website. Capital Q is the source charge, Q0 the test charge. Vp is the potential at point P inside the field. So the formula, the mathematical formula for electrostatic potential at point P is represented by Vp, which is equal to W by Q0. The SI unit of electrostatic potential is Joule per Coulomb. So this is a very important formula which you have to remember the moment we say about electrostatic potential. This electrostatic potential difference is the potential difference between any 2 points inside the electrostatic field. Let us assume that 2 points inside the electrostatic field is x and y. And if Vx minus Vy represents the electrostatic potential difference between the points x and y, then the mathematical formula for potential difference is Vx minus Vy is W by Q0. And this Yx represents the amount of work done to bring a unit positive charge from Y to X. Vx minus Vy. Vx is at greater potential. And that is the reason we represent as Vx minus Vy is W from Y to X divided by Q0. So this is about electrostatic potential and electrostatic potential difference. Hope it is very clear to you. The second question is how to represent electrostatic potential at the same point in terms of source charge Q as given in the diagram. All the parameters, capital Q, the source charge, point P where we have to find out the potential at point P and in terms of the source charge. And the 2 points A and B. The distance of point A from source charge is x and the distance between AB is dx. Here, since the source charge is positive, the test charge will experience a repulsive force. That is the reason why the force we have represented along this direction. This F is Coulombs force. This F is electrostatic force or Coulombs force. And the direction of force, it is away from Q naught. Why? Because it is experiencing a repulsive force. And the source charge is positive. Now, here all the parameters are very well defined about plus Q, Q naught, R, X, F, the electrostatic repulsive force, Vp, the electrostatic potential at point P, and W from infinite to P means the net work done to take unit positive charge from infinite to point P. As I already told you, the root formula about electric potential. The first equation is represented by potential at point P is W by Q naught, which is equation 1. Now, we have to find out what is the net work done to take or to bring the charge from infinite to point P. Again, we have to use the concept of calculus because here the function that we define here, it is a continuous varying function. This force is a continuous varying function. We cannot use the concept of summation to find the net work done to bring the test charge from infinite to point P. Why? Because F is continuously changing. It is a continuous varying function. Now to find out the net work done, we are going to use the calculus method. First, we find what is the small work done to take the charge from point A to point B. Point A at a distance of x from plus Q and the distance between AB is dx. So the small work done to take the charge from A to B is the dot product of force vector and displacement vector. Work done is a scalar quantity, that is why it is a dot product of force and displacement vector, which we have learned it in 11th class. The direction of force, it is along this direction, and the direction of dx, it is opposite to the direction of force because we are doing work to take the charge from A to B. So here the angle between force and dx is 180 degree. So when we use f dot dx, the dot product formula is f dx cos theta. And why the dot product? Because work done is a scalar quantity and dot product is a scalar quantity. So theta is 180 degrees. So here cos 180 is minus 1. So minus fx. So dw is minus fx, which we represented as second equation. Also we know this force is Coulombs force. The Coulombs force which acts at point A, It is K, dielectric constant, capital Q, Q naught, divided by x square, because point A is at a distance of x from source charge. So this is Coulombs force represented. Now we are going to substitute this Coulombs force in this equation. So dW is K, capital Q, Q naught by x square into dx. So we are going to integrate to find out the net work done. The net work done to take the charge from infinite to point P is given as by integrating dW. On integrating and placing the limit is from infinite to point P, and point P it is at a distance of r from source charge. So here we get the work done as K, capital Q, Q naught by R. This is the fourth equation. Substituting this fourth equation in the first equation means we got what is the net work done. So net work done, substitute it here. After substituting, this Q naught will get cancelled. So this is the electrostatic potential at point P in terms of source charge. So when you get in your question to express potential in terms of source charge Q, you will be doing this solution. Again, it is very clear. This potential is inversely proportional to the small r. Here it is small r. It is represented here as written as capital R. Actually, it should be small r. So this explains that this electrostatic potential, it decreases with distance. So V is inversely proportional to R. So when we sketch a graph taking R along y-axis and potential along the R along x-axis and potential along the y-axis, the nature of the graph is in the same way. So this is the second question, electrostatic potential in terms of source charge. Hope both the questions are very clear to you. Next it is, the third question is how to find electric potential at any general point at distance r from the center of a dipole. Now, what is this electric dipole? Already we have learned in the first chapter. Dipole, it is a system of two equal and opposite charges, that is minus Q plus Q, separated by a small distance 2a. And as we know, the direction of the dipole moment is from minus Q to plus Q. So hope this electric dipole, you know what is electric dipole. Electric dipole means it is a system of two equal and opposite charges separated by a small distance. And what is electric dipole moment? It is the product of the magnitude of either charge and the separation between the two charges. Here the separation is a vector quantity and it is directed from minus Q to plus Q. That is why dipole moment is a vector quantity which is directed from minus Q to plus Q. So here the question is to find potential at any general point. So in the diagram, this is the dipole, point P is the general point, and the distance of point P from the center of the dipole is R. So we are going to find out potential at point P. Potential at point P will be equal to the sum of potential at point P due to minus Q and the potential at point P due to plus Q. Here we use the superposition principle. It is the potential at point P due to multiple charges. Here it is not multiple charges, it is two point charges. So the diagram here, O is the center. The distance of point P from O is R. The distance of point P from minus Q, it is R1. The distance of point P from plus Q, it is R2. Theta is the angle which this R making with the direction of the dipole moment. Children, it is very important to know what is the direction of the dipole moment. The direction of the dipole moment, it is directed from minus Q to plus Q. So, theta is the angle between vector R and the direction of the dipole moment. Again, there are two methods to derive this. One is a little, it's the analytical treatment. And this is the method which even is given in the NCERT textbook, and it is simple. A slight assumption is there which you have to understand. So here this completes the diagram. When I draw a perpendicular from point B to this AB, and since a dipole is a very small dipole, this difference, that is from here to here, the difference is R1 minus R2. If I consider this as n, this an is R1 minus R2, and this difference is very small. It is not very small, it is not equal to 0, but it is nearly equal to 0. That means this is a very small difference. In the diagram, it seems that the difference is big, but actually it is not a big difference because dipole normally is a short dipole. So all the parameters as I explained here to weigh the separation between minus Q and plus Q of electric dipole are distance of point P from center O, theta the angle between OP making with the dipole moment P, R1 distance of point P from minus Q, R2 distance of point P from plus Q at point B. V1 potential at P due to minus Q, V2 potential at P due to plus Q, and V the net potential due to dipole, V is V1 plus V2. Where V1 will be then minus KQ upon R1 because at point A is minus Q and V2 is KQ upon R2. It is convenient to take minus Q on the left side and plus Q on the right side. So after substituting for V1 and V2 in this equation, we get it as V is KQ, R1 minus R2 divided by R1 into R2. As I already told you, this R1 minus R2 is very small. And when we use the trigonometrical concept, this R1 minus R2 is approximately equal to AB cos theta. And so in this R1 minus R2, we represent it as AB cos theta, and where AB is 2A. And R1, R2, it is approximately equal to R square. Approximately equal to R square. So after substituting here, KQ 2A cos theta, this is KQ, R1 minus R2 is 2A cos theta. So by the trigonometrical concept, we get it, this R1 minus R2 as 2A cos theta. Why? Because in this right angle triangle, A, this is N and B. In this A and B, this angle theta, so this angle also is theta, because nearly all the three lines will be parallel. I told you assumption is there which it should be very clear to you. You have to think it by yourself also. So here it is when we use that, and this AB is 2A. So cos theta, it is equal to R1 minus R2 base, and this is the hypotenuse which is divided by 2A. And that is how we get it as R1 minus R2 as AB cos theta, and AB is 2A. So when we substitute here, this V comes out KQ 2A cos theta upon R square. Q into 2A is dipole moment, which in first chapter we have learned it. Again, Kp cos theta. Cos theta means it's a scalar product, isn't it? Means Kp cos theta. So when we multiply by this vector r divided by r, so we can write in form of dot product, that is vector p dot vector r. So this is the general expression for the potential at a point, at any general point due to electric dipole. Kp cos theta upon r square. See the difference. In the second question, potential at a point due to a source charge, it was kq upon r, simply r, kq upon r. Denominator was r, is r there. And due to a dipole, it is kp cos theta upon r square. So V is inversely proportional to r square in case of a dipole. Again, different cases. The first case, when this point P lies on the axial line of the dipole, that is, we have taken this point P as the general point. Now when this point P lies on the axial line of a dipole, that means along at any point along the direction of the dipole, say here. So what happens, this theta becomes 0, or theta is 180 degree. So in that case, it is V plus minus Kp upon r square. That is, the potential has greatest positive or the greatest negative value. Second case is when point P lies on the equatorial line of the dipole. Where is the equatorial line? It is when point P, it lies on the perpendicular bisector. This is the equatorial line. So if this point P lies on the equatorial line, theta is 90 degree. So when theta is 90 degree, cos 90 is 0. So if this point P lies anywhere along the equatorial line, the potential at point P is 0. So this type of questions or this type of cases, you can get it either for MCQ or in fill in the blanks or in one word answer. So you have to learn it very well. So this is about potential at any general point due to a electric dipole. Then again, as the fourth question is electrostatic potential at a point due to a group of electric charges, which you have learned it in the first chapter also. Field at a point due to multiple charges. Force at a point due to multiple charges. In the same manner, potential at a point due to multiple charges. Let the multiple charges be Q1, Q2, Q3 and so on to Qn. Or here we have taken it as Q5. Distance of Q1 from P is R1 and the distance of Q2 from P is R2 and so on, like that. Again, using the concept of the superposition principle. Potential at P due to charge Q1 is KQ1 upon R1. Potential at P due to other charges, the similar manner. Superposition principle, we get the potential, the net potential at point P due to the multiple charges as K Qi by Ri, where I represents summation I 1 to n. Here we use the summation because all these functions are discrete values, specific values. So these 4 questions Children, you learn it very well, and in the next class I'll tell about the next 4 questions. So these 4 questions you learned very well, and thank you children for this.